Welcome back from the intermission. This is part 2 of the introduction to hydraulic cylinders.
I find more and more that there's some kind of mystery associated with pneumatics for some reason. I take pneumatics for granted because I think I was first introduced to pneumatics in Legos, and that's kind of where I got my interest in them, probably. So anyway, enough nostalgia. But I just wanted to kind of show you the basics. It's not complicated. It's very straightforward. There's multitudes of different ways of doing different things with pneumatics. You can have a lot of fun with pneumatics. You can make catapults. You can make can crushers. You can make animatronics to scare the kitties in the yard on Halloween, which is kind of one of my personal favorites. So anyway, so what you see is just a small sample of what's out there as far as pneumatics. Pneumatics basically is just like hydraulics on a tractor or construction equipment. You basically take a medium and you force it into a cylinder, in this case air, and so if air comes in this bottom inlet right here, there's a piston inside this sleeve, and it forces the piston to rise, so the air volume fills up the bottom of this chamber. This is a dual acting cylinder, meaning that I can push air into it and make it extend, and I can also push air into it and make it retract. So when it extends, air is going in the bottom, it forces the piston up. When it retracts, air goes in the top and it forces the piston back down. And that's simply it. You may see a cylinder that only has one inlet, and that means it's a single acting cylinder, or sometimes a spring return cylinder. If you've seen the chop saw clamp that I made, that's a spring return cylinder. You give it air, it extends. When you take air away, it naturally retracts because of the spring. The spring is taking place of the dual acting part of the cylinder, meaning that you don't have to induce air into the system to make it reverse the action that it just did. The spring does that for you. So if you've seen on my other channel, the channel name is Radio Shack 7, but that's my CNC related site. You've probably seen this rig before in some fashion like this. This was actually the blind nut installation tool that I made for my CNC machine that would draw the nut into the bottom of the table. And you basically just actuate this and it sucks it up. This is a different kind of switch. It actually is a dual position switch. When it's resting, the way I've got it plumbed, it naturally extends. And so when I counteract that, it sucks it up. And then when I let it go back home, it extends again. It does have a second position where I can push it forward, but that doesn't do anything in this scenario. Just one example. These are usually called pancake cylinders because obviously they kind of look like a pancake. This one drives that point home even more. This is made by Bimba, and it's a flat cylinder. Very little force, or no, I'm sorry, not force, very little extension from the cylinder. I'm not even sure what it is. It might be a ½ inch or so. But this would be great for like a clamping fixture or something to where the movement isn't that large. You just need the pressure behind it. With this blind nut installation tool that I made, I believe I was running it at about 100 psi, and you could actually see the MDF pull up. So it was probably a little bit more, but it definitely did the job as far as installing those blind nuts as quickly and straight as possible. Some of the brand names I've got here, Bimba, Festo, SMC. This is an interesting little cylinder. It's kind of a smaller bore, but I do have these pressure adjusters or airflow adjusters that are on it, so you can dial in how fast or slow it extends or retracts. This is a non-rotating cylinder, so instead of it being round here, this is actually hexagonal, so it cannot turn. I used this on one of my first Halloween props, and it's for a low volume, you get a lot more bang for your buck as long as you're not trying to move a lot of mass. It doesn't require a lot of air to run that cylinder, so that's good. This is a Festo rotary cylinder. by default, it returns to in between 0 and 90 degrees. So right now it's at 45 degrees. If you give it air one way, it goes full, let's say 90. If you give it air the other way, it goes to 0. This has hydraulic dampers in it instead of pneumatic dampers to where you're adjusting the pressure or you're adjusting the flow rate. This actually has hydraulic dampers so that when it starts to turn, it hits a point to where it cushions the blow. It's hard to talk about, can't really show you. I can feel it as it moves easily, and then it engages the hydraulic damper, and that just slows it down to give it a cushion stop in both directions. Could be fun for Halloween as well. This is the one I showed you a minute ago. Very simple, much like the SMC. This one has a round shaft, so this whole piece can rotate. There may be installations where you need to make sure that does not happen, and that's where a non-rotating cylinder would come into play. I believe I got all of this stuff off of eBay, and usually you can find these things in lots. You might pay $10 or so, and about that much in shipping, but you'll end up with 5 or 10 different actuators of different sizes. And if you're just looking for a grab bag of parts to just do some oddball things around the house or animatronics or whatnot, you may find what you need. This is probably the biggest in girth cylinder I have. This thing is huge. I've had to plumb it down to 3/4 just to get it usable for me. It does have valves on each end, and it's a massive cylinder. You can move a lot of weight with that. I made a pop-up ghost with this one time, and I think the sound alone was enough to scare everybody. Real quick, on the valve side of things, you've seen me use things like this if you saw the Halloween videos. This is just an electronic way of doing the same thing that I'm doing with this switch right here. Basically, air comes in, and depending on whether this coil is energized or not, meaning whether you're applying power to this or not, the air is going to go one way or the other. So this would easily be able to activate or actuate one of these pancake cylinders, because I've got 2 ports and 2 ports on the switch or on the pneumatic valve. So one would be up, one would be down. So anyway, hit me up if you have any questions. Very straightforward. These things are a lot of fun. Always be careful with them. If you have one of these, one thing I'll tell on myself. One thing that I run into from time to time is, because I buy a hodgepodge of different pieces off of eBay or what have you. There's no standard to the sizes of the plumbing fixtures. I've got a horrible mix of standard and metric, and there's a big difference in 6mm and 1/4 inch when it comes to pneumatic fittings. If you try to put 6mm inside a 1/4 inch and you give it some pressure, you might want to look out. So just food for thought. But anyway, like I said, if you have any questions, hit me up. And I hope everybody's doing well, and we will talk to you soon.
Now that you have a better idea of the types and styles of cylinders, let's consider how they are applied within different designs. Consider for a moment how the human body is designed. Your body's muscles are essentially single-acting cylinders, which are capable of retraction only. Each muscle group has a matching muscle that counteracts the original muscle. If we were to design a backhoe arm using single-acting cylinders, it would require a second cylinder to be mounted underneath the arm. Notice how this would restrict motion due to making room for the cylinder. Here's an example of the design of a backhoe if double-acting cylinders are used. Notice how compact this arm can fold up. Before we start drawing the cylinder, let's take several apart in order to help define some of the terminology used. Start with a single-acting cylinder. There is the ram, or a piston and shaft, retaining nut, glands, and a port. Here is a cutaway view of a double-acting cylinder. Notice that the major components have not changed. Only more components have been added. The major change is a second port, which allows fluid to be pumped in to the other end. Additional items such as wear bands, seals, and O-rings help prevent dirt from entering the cylinder. This is what the sectioned engineering drawing of that cylinder might look like. Notice the additional seals and bushings. Notice the end caps on this cylinder have tie rods that protrude through them. Other models may have flush-mounted rods that don't protrude. An alternate design is shown on these cylinders, which have welded-on end caps. Let's compare some of the advantages and disadvantages of each type of end cap. The advantages of a welded-on end cap are fewer components are required. It's stronger. It's also easier to fabricate and not as bulky. A tie rod style end cap has the advantage of being easier to disassemble in case of repair. However, this style has the disadvantage of a higher parts count and therefore a higher cost. That's right, more parts means more money. This brings up an interesting concept. All engineering is a compromise. It is the engineer's job to strike a reasonable balance of performing the required functions, being reasonable to repair, at the lowest cost possible so as to not waste money. One such design compromise is to use a threaded-on end cap that screws into place. The threads may be a little difficult to see in this photo. Also, notice the addition of a clevis and a pin eye for mounting in the cylinder. It has the advantage of being easy to disassemble in case of repair, but doesn't require additional parts. However, it does require additional machining steps, so more processes result in more money. In order to aid the engineer in finding a reasonable compromise, the technique of taking a long-term view of a project will often help in determining these goals. For instance, considering the cost over the lifetime of the equipment, which includes disposal costs at retirement, will help determine which components are used. The engineer must consider the long-term performance, which includes ease of repair or maintenance. These are balanced against the initial cost or purchase price of the component. Here is a quick review of the concepts presented so far. Form follows function. This concept from biology determines how a part is shaped. Depending on their function, cylinders may be single or double acting. End caps may be tied on, welded on, or threaded on, also depending on their function. More parts mean more money. More processes also means more money. Engineering is a compromise. In order for the engineer to design a winner, they often must consider the long-term functionality of the part.